Alright, Assalamu alaikum. This is Salah bin Nadeem, and we are recording the fourth video lecture video tutorial for the topic of the carburetor. And as I mentioned in the last video tutorial that we have completed the theoretical portion of the topic carburetor, and now we will do the derivation for the calculation for the relation of the air fuel ratio. So we will start from here today. First of all, if we in order to calculate the air fuel ratio, we have to determine the relation for the mass flow rate of air, and not only for the air only, but also for the mass flow rate of the fuel as well. The mass flow rate of the fuel which is moving from inside the float chamber into the venturi throat through the fuel metering orifice. So we would be basically finding out two relations, one for the mass flow rate of the air and second for the mass flow rate of the fuel. Then we will simply divide them. We will take the ratio between them, and as a result you will get the relation for the air fuel ratio of which is being prepared inside the carburetor. Okay, starting now with the formulation for the mass flow rate of air. For example, a simple carburetor with the tip of the fuel nozzle h meters above the fuel level in the float chamber. It may be noted that the density of the air is not same at the inlet of the carburetor and the venturi throat. So another point, in this paragraph, basically there are two things which needs to be understand here. The first one is basically that we are not neglecting the density change of the air from the carburetor, from the inlet of the carburetor to that section of the nozzle at which the fuel is being taken in, or you can simply say into the venturi throat. We will consider the difference in the densities of these two sections. So we will be doing the two derivations. First one is when we are not neglecting the compressibility effects. Second one, when we are neglecting the compressibility effects, or you can say when we are considering air as an incompressible fluid. So we would be doing this derivation two times, and for the second case, when we are considering air as an incompressible fluid, this relation will be quite easier as compared to the relation which we are doing now. Another thing which needs to be understand here is that the tip of the nozzle is h meters, or you can simply say I will use z meters here. Here you can see that the difference between these two levels is z. Z is basically the difference between the fuel level at the float chamber, fuel level inside the float chamber, and that section where the fuel metering orifice is. So the difference between this level is Z. Okay, consider this as Z. So we will first of all we will determine the mass flow rate of the air when we are taking the change in velocity into the account. What we will do is we will simply apply the steady flow energy equation at the inlet and outlet section. This is the inlet section of the carburetor and this section is the second section, which is the inlet of the Venturi throat. So air is coming in from this direction and then entering, then going to the Venturi throat, and we are applying the energy equation at this between these sections. So we will take the energy heat coming in and heat going out between this process. Then the second portion in the energy balance equation is of any work done by the system or on the system, and then the third section is of any energy changes which is in a result of the mass which is coming inside and going outside of this carburetor, of this circular section of the carburetor. Then we have the next expression is for the enthalpy changes, and another one is for the these changes for the kinetic energy changes. You must keep this in your mind here is that H here is for enthalpy. That's why for the elevation I am not using the letter H. We will be using the alphabet Z, which I mentioned in the diagram. So H is for the enthalpy changes. Okay, now since the flow which is going in, the airflow which is going inside the carburetor and going outside the carburetor, there is no heat which is coming into the system and going out of the system. Similarly, there is no work done into this there is no work done by the system or on the system, and there are no energy transfer with the flow of the air as well. So all of these terms on the left hand side of the energy balance equation will be zero in this case, because we are assuming this as an adiabatic process. So there will be no heat transfer and no work done and no energy changes as a result of the airflow. So we will only be having the enthalpy change and the enthalpy changes and the kinetic energy changes in this energy balance equation. Similarly, one more thing which needs to be understood here is that C2 is the velocity of the air at the Venturi throat and C1 is the velocity of the air at the inlet, or you can say at the section AA. At this section the velocity is C1 and enthalpy is H1. At section 2 the velocity is C2 and enthalpy is H2. At this section, at section AA or state 1, the speed of the air is very small as compared to the speed of the air at section 2, because at section 2 kinetic energy has been increased as a result of the decrease in the pressure, because we have a venturi at section 2. We have a venturi throat at section 2. So the air has passed through the venturi and the pressure energy has been converted into the kinetic energy. So the speed would be very high at section 2 as compared to the section 1. So we would be neglecting C1, because the nozzle's inlet velocity is very small as compared to the velocity at the venturi throat. Now we would only be left with C2 H2 minus H1, and when we rearrange this and this Q minus W, all the terms on the left side would be 0, because we have an adiabatic process. So when we shift this H2 minus H1 on the left side, it will become H1 minus H2. This 1 upon 2 would then go on the left side to multiply with this H1 minus H2, and then we will simply take the square root to obtain this relation. I hope this is clear now. We have simplified this steady flow energy equation into this C2 is equals to under root 2 H1 minus H2. Because we have assumed adiabatic process, so all the terms on the left hand side would be 0. Since the velocity at venturi throat, which is C2, is quite higher as compared to the velocity at the inlet of the carburetor, so C1 is considered as 0. And when we rearranged this equation, we would obtain this relation, which is C2 is equals to under root 2 times H1 minus H2. Another thing which needs to be understood here is that we were talking about the heat, work and energy which is coming in and out with the mass, with the flow of the air. And on the right hand side we had mass which is being multiplied with the difference in the enthalpy. But in the next step the mass is not present, because we have simply sent this mass on the left hand side, and instead of having the heat energy or work energy, we basically had energy per unit mass. And since we have an adiabatic process, we do not have any sort of energy changes, and we do not have any work as well. So these terms will be equal to 0. Okay, so another thing which needs to be understood here is air is behaving like an ideal gas, and for an ideal gas we have these relations. Cp times T, and similarly if we are talking about a constant volume process, then we have relation this. Means H and U, enthalpy and internal energy, can be represented as in the terms of temperature if the working fluid, which is air in our case, is if the working fluid is comparable, or you can simply say the working fluid is considered as an ideal gas, which we are considering in our case right now. So we will simply replace this H with Cp multiplied by T. So when we replaced H1 with Cp multiplied by T1 and H2 with Cp multiplied by T2, we will take Cp as common, and as a result we will get this relation, which was under root 2 times H1 minus H2. It will be simplified into under root 2 times Cp, 2 times of Cp multiplied by T1 minus T2. So right now we have obtained a relation for the speed of the air at the Venturi throat. Now, since the flow process from inlet to the Venturi throat can be considered to be an isentropic process, as you have studied in the last semester in the subject of the thermodynamics, that nozzles and diffusers are basically isentropic devices, and there are no and there will be no change in the entropy. There will be no change in the entropy in the flow inside the nozzles and diffusers. So we are basically considering that effect in the Venturi throat of this carburetor, and we are applying the isentropic relation at state 1 and 2. And in the next step we will simply multiply this T2 upon T1 from 1, and when we are doing this we will also do the same thing on the right hand side, and we will subtract this P2 upon P1 to the power gamma minus 1 upon gamma from 1. Then in the next step, in the left hand side we will take the LCM, and this term will become T1 minus T2 divided by T1, and that T1 would be sent on the right hand side, so that it will be multiplied with the other factor which was already present on the other side, on the right hand side. Now we have determined a relation for T1 minus T2 which was present in which we required for the speed at the Venturi throat. We will replace it, and as a result we get this relation in terms of the pressure for the velocity at the Venturi throat. So now, since the mass flow rate of the air would remain same from section 1 to section 2, because we have a steady flow device, a nozzle which is a steady nozzle. Our nozzles are a steady flow device. Now we are also, as I mentioned earlier, that we will consider the air as an compressible fluid in the first case. We have determined the relation for C2. Now we require a relation for the density at state 2. E2 is the design parameter which manufacturers already know, but C2 and rho 2 but the relations for C2 and rho 2 are required in our case. We have determined the relation for C2. Now we have to determine the relation for rho 2, and then we will multiply these three factors to obtain the mass flow rate of the air. Now multiplying, so in order to determine the density at state 2, we have an isentropic process. We are considering this relation. This is an isentropic relation for the pressure and volumes. We will simply convert this specific volume, and you can clearly see here that I have mentioned the volume in terms of a specific volume. I have divided the volume with the mass on both sides. So we are talking about the specific volumes here. So now this specific volume is converted into the density in the next step on both sides. As you may know that densities is equals to mass upon volume, and when we are talking about specific volume, specific volumes are volume divided by mass. So when we compare these two relations, the specific volume can be taken as the reciprocal of density, 1 upon density. So we have replaced this specific volume with the density on both sides. Now rearranging this equation and making rho 2 as a subject to obtain the relation for the density at state 2. Now we have a relation for the density at state 2. Similarly for the velocity at state 2 as well. We will simply replace the density and velocity in this equation to obtain the relation for the mass flow rate of air, and this will be the case here. Here you can see that I have replaced rho 2 and also C2. So now another thing which when we go to next step, here you can see that this rho 1 is changed into P1 upon R times of T1. This rho 1 is converted into P1 upon R times of T1. So here you can also see that, as we know, PV is equals to mRT, and when we divide this volume with the mass, it will become P times specific volume times RT, and when we convert this specific volume into density, we will get a relation like this, and when we rearrange this, so we will get P upon RT. Since we are talking about state 1, so pressure and temperatures of state 1 would be used. The gas constant R will be remain constant here. So we have replaced this density with P1 upon R times of T1. Now another thing in the next step which we need to understand here is, we are taking this P2 upon P1 to the power 1 upon gamma. inside the square root. We are taking this p2 upon p1 to the power 1 upon gamma inside the square root, where the power of this p2 upon p1 would become 2 times 2 upon gamma, because it is inside the square root. And then we will multiply this p2 upon p1 to the power 2 upon gamma with 1 and with minus p2 upon p1 gamma minus 1 to the power gamma. And as a result, when this factor is gone inside the square root and multiplied with this factor, we will obtain this relation p2 upon p1 2 upon gamma, p2 upon p1 gamma plus 1 upon gamma. So another question will be how this gamma minus 1 upon gamma is converted into gamma plus 1 upon gamma. Answer is very simple, that when these factors are multiplied, p2 upon p1 to the power 1 upon gamma, p2 upon p1 to the power gamma minus 1 upon gamma. Since the bases are same, their powers will be added to each other. And when we add these powers, so 1 upon gamma plus this will be 2 upon gamma, since it is gone inside the square root. Since the bases are same, LCM would be gamma. We have simply taken the LCM here, then this will become gamma plus 1 upon gamma. This was a simple calculation, that how this gamma minus 1 upon gamma has become gamma plus 1 upon gamma. I hope it is clear to you that how this p2 upon p1 to the power 1 upon gamma has gone inside the square root, and when it is gone inside the square root, its power will become 2 upon gamma. Then it will be multiplied with 1 and the other factor which was present inside the square root, inside this brackets, and then you will get this relation. So another thing which needs to understand here is of this temperature. The temperature which was present inside the square root has now came outside the square root, and I have simply represented as the under root of p1 because they are being multiplied with each other, and I have simply mentioned it separately. And when we in this temperature, as we know that when root T and root T is multiplied with each other, we will simply get temperature. So what I have done here is I have broken this temperature T1 into root T1 and another root T1. So now we have 2 root T1 and T2 in the denominator, and 1 root T1 would be cancelled out with the root T1 which is present in the numerator. So we would be left only with the 1 root T1 in the denominator. So I hope it is clear that how we have obtained the relation for the mass flow rate of the air. And I know the calculations are a bit complex, but once you will practice it, it will be quite you will come to know that these calculations are quite easy, and they are not very much difficult. There are only 1-2 things which needs to be understand here. One is the factor that we are taking this p2 upon p1 to the power 1 upon gamma inside the square root. When it is going inside the square root, the power will not remain 1 upon gamma, it will become 2 upon gamma because it is going inside the square root. And when it will be multiplied with the terms which is present inside the brackets, one will give you the exact same thing. However, when on the other side the bases are same, so the powers would be added, which means that 2 upon gamma and gamma minus 1 upon gamma would be added to each other, and as a result you will get gamma plus 1 upon gamma as a power. Okay, so now as I mentioned earlier that we will determine the two relations, one which is for the mass flow rate of the air and other one which will be for the mass flow rate of the fuel. So now we are going but before we go to the calculation of mass flow rate of air, here we have some constant like Cp, R, we have and gamma, Cp, R and gamma, we have some constants here, and when we replace the values of these constants we will get this relation. And this whole factor is being, instead of writing this complete factor over and over again, it is simply represented as phi. Okay, another thing which needs to be understand here is this is the relation for the mass flow rate of air, and it is an ideal equation. But actually there will be a lesser mass of air which would be going inside the venturi section of the carburetor, and in order to incorporate such effects we would multiply this term with the coefficient of discharge of the venturi, coefficient of discharge for the venturi, which is CDA, discharge coefficient, and A basically, A in the suffix basically represents air. So CDA and 0.1562, they are all similarly the area as well. Area for one carburetor will remain constant. We converted this into the proportionality, and we simply came to know that mass flow rate is directly proportional to the atmospheric pressure, and it is inversely proportional to the atmospheric square root of the atmospheric temperature, and directly proportional to this factor, which we represented simply as a phi. So now we have determined the relation. We have determined the relation for the actual mass flow rate of the air. Now we require another relation which is for the mass flow rate of the fuel. Since fuel is an incompressible liquid, we can simply apply the Bernoulli equation on the fuel. And for the fuel, the state 1 and 2, I am using this color for the fuel. This is state 1 for the fuel. Inside the float chamber, this is state 1, while the state 2 will remain same for fuel, because it is going inside the venturi throat. So state 2 will be same, but the state 1 will not be at the entry where the air is present, but it will be inside the float chamber, and inside the float chamber there will be some pressure which would be exerting on the fuel, but there will be the velocity of the fuel at the inside the float chamber will be 0. So C1 will be 0, there will be some pressure P1, and in the venturi throat there will be some pressure, and also there will be some velocity as well. And there is elevation difference, which I mentioned in the beginning of this derivation. There will be the elevation difference which we are simply representing as Z, because we have considered the datum at this point. So there is no Z1 because Z1 is existing at this datum point. This section is however a little above the datum, so there will be a difference at state 2, but state 1 is existing at the datum, so z1 will be 0 and z2 will simply be written as z. So applying the Bernoulli equation, since the velocity inside the float chamber is of the fuel is 0, inside the float chamber is 0, there is no kinetic energy, we are writing it as 0, and the datum is also at z1, so there will be no elevation of the fuel level inside the float chamber. However, there will be some pressure present. Now we will simply send this P2 upon rho f on the left side, where it will simply subtract with it, and we will get P1 minus P2 upon rho f. Then this Gz would be sent on the left side for the subtraction, and the 2 which is present in the denominator would then go to multiply with this whole factor. Then we will take the square root to obtain the relation for the speed of the fuel. Okay, so now we have obtained the relation for the speed of the fuel. Now again, the area of the fuel metering orifice is basically a design factor. We do not require to determine any relation for that. And similarly, the density of the fuel, this density of the fuel is also, since the fuel is incompressible fluid, so there will be no change in the density as well, density of the fuel as well, so it is also a constant, so there is no need to determine the relation for that as well. We were only required to determine the relation for speed of the fuel, which we have already determined it. Then we simply replace it and rearranging it to form this relation of mass flow rate of fuel, which is area of fuel metering orifice multiplied by square root 2 times the density of fuel, P1 minus P2 minus Gz rho f. Since this is the relation for the mass flow rate of fuel, for ideal mass flow rate of fuel, and in order to obtain the actual mass flow rate of fuel, we will simply multiply it with the coefficient of discharge of the fuel. Now, in order to determine the relation for the air fuel mixture, air fuel ratio, we will simply determine the ratio between the mass flow rate, actual mass flow rate of air to the actual mass flow rate of fuel. When we replace them, we will get the relation for the actual mass flow rate of fuel. So this was the derivation, this was the relation which we were asked to obtain, and it's a bit complicated relation and required the number of formulations as well. If I simply explain you the pattern which we have to follow is, first of all, we would obtain relation for mass flow of air, then for mass flow of fuel, then we will determine the air fuel, the relation for the air fuel ratio. But in order to determine the mass flow rate of fuel, you were required to calculate C2 and rho 2 as well. This is not pressure, this is, I am talking about the density at state 2. Similarly, for the mass flow rate of fuel, you were only required to determine the C2, which is speed at state 2. We do not require the density 2 of the fuel because fuels are incompressible and their density will remain same. So this was the flow for the first derivation. When we are considering air as an incompressible, when we are considering air as a compressible fluid, okay, because the density is changing, so it will be a compressible fluid. So now we come towards the simplest derivation, which is for the relation of the air fuel ratio when we are neglecting the compressibility effects of the air, or you can simply say when we are considering air as an incompressible fluid. And since we are considering air as an incompressible fluid, we will simply apply the Bernoulli equation and we will get this relation, and we will rearrange it to obtain the relation for C2, which is this. And when we since now we have obtained the relation for C2, and now since we need to determine the mass flow rate of air, we will simply put C2 in this relation, and you will note that the density of the air will remain same. So the relation which we did to obtain the relation, so the calculation which we did to obtain the relation for that rho 2, we do not require to do those calculations here. Now we put the formula of C2 which we obtained earlier, and when we rearrange this, we will get this relation. You will see for the actual mass flow rate, we have also multiplied it with the coefficient of discharge of the air as well. This is the formulation, this is the relation which we have obtained for the actual mass flow rate of air when we have considered air as an incompressible fluid. Now we are again required to do the calculation for the fuel, for the mass flow rate of the fuel, which we have done in the previous derivation. So I am not going to repeat that part again. But when you are asked in exam, you will have to do that. Means in the exams you can be asked to derive the relation for the air fuel ratio for when air is considered as an compressible fluid. So you will have to do the first derivation, in which you have to calculate these sections, all of these things. But when we are talking about the second derivation, you are required to do all these things. You would be you will calculate, you will derive the relation for mass flow of air, for the mass flow of fuel as well, and then you will do the calculations for the air fuel ratio. But the difference will be, in order to obtain the mass flow rate, you will only require to calculate C2, because there are no changes in the density, and the calculation for the C2 would be very much easy as well, because in the first part, in the first derivation, air was considered as a compressible fluid. You cannot apply the Bernoulli equation on the compressible fluids. And in the second derivation, air is an incompressible fluid. You can apply the Bernoulli equation on the incompressible fluid. So in the second derivation, we have simply determined the mass flow rate of air. We have simply determined the C2 by using Bernoulli equation. But in the first derivation, we determined the speed at section 2 C2 by using energy balance equation. So you have to keep this in the mind, that when air is considered as a compressible fluid, you will do energy balance, you will use energy balance equation. When air is considered as an incompressible fluid, you will use Bernoulli equation. So other things, and the part for this part will remain same for the both derivations. Then you will simply divide these relations to obtain the ratio for air fuel ratio. So this is the relation for air fuel ratio. And when we are considering that there is no elevation effect, or let's say this venturi, this fuel metering orifice, which was Z meters above this datum point. Let's say if I draw the datum point, this is your datum point, and this one here is the level. This is the level of the fuel metering orifice, or the pipe from which the fuel is flowing into the venturi throat, when they are at same level. So Z would be 0. Z would be 0 when this section is here on this blue line as well, on the datum as well. So for such cases Z would be equal to 0. Another thing which you need to know here is the fuel metering, the level of the fuel metering orifice, the outlet of the fuel metering orifice is either at some elevation, which is shown in this drawing, some elevation which I said Z elevation, or at the same level of the float chamber. It will never be, means this section, this nozzle will never be below, means it will not be like this here. If it is below the float chamber level, there will be some dripping effects, means pressure is exerting on this section, so there will always be some fuel which is going outside this fuel metering orifice. So this fuel metering orifice is either on the same level, but usually it is always some small distance, some centimeters, some millimeters above the level of the fuel inside the float chamber. So you have to keep this in your mind as well. So now we will just conclude the derivation. When the Z is 0, we will simply, this factor will become 0, and then P1 minus P2 and P1 minus P2 in the denominator would cancel out with each other, and we will simply be remain with rho 1 upon rho f inside the square root. So this will be the relation for the air fuel ratio when for the incompressible fluids, when the air is considered as incompressible fluids, and not only when the air is considered as incompressible fluid, but also the fuel metering orifice is at the same level as the fuel inside the float chamber as well. This is relation for the air fuel ratio when air is considered as incompressible fluid. Incompressible fluid only. And this is the relation when air is not on, where air is considered as incompressible fluid, and not only that, but also the level of the fuel metering orifice is same as the fuel inside the float chamber, or you can simply say when there is no z, or z is equals to 0. So this is all from my side for regarding the derivation. There were two derivations, and you can in the exams you can be asked with the one of them or maybe with both of them. So they are not very difficult. You only require to do a practice. If you solve this derivation one time, you will say that this derivation is very easy to understand and very easy to solve. In the next class we will do some numericals regarding the topic of carburetor. So in case if you have any query regarding the previous three lecture of the carburetor and this lecture of the carburetor, this derivation as well, you can always contact me, you can always ask me. See you in the next video, and we will solve some numericals. Then we will conclude this topic of the carburetor. Okay, Allah Hafiz.